I'm in the middle of building my own homebrew 8-bit CPU. This has been a very fun and exciting project, but when it comes to executing programs on the CPU, one annoyance is that we have no way of displaying information that is easy for a human to read. Instead, I've been staring at the binary values in the registers displayed on the LEDs to figure out if the CPU is doing the correct thing. I would rather use one of these liquid crystal displays and have the CPU print some interesting information on it. This particular model is a 2004A version 1.4, which is a very common display module that you can get pretty cheaply from almost any online electronics retailer. The 2004 indicates that the display has 4 lines with 20 characters each. And these displays are pretty easy to interface with. They need a 5-volt power supply and a contrast voltage, and then they have 3 control signals and 8 data signals, plus 2 connections for the backlight, which lines up nicely with an 8-bit CPU. Almost all of these display modules use a 4470 display controller internally. This chip can interface with the CPU or a microcontroller on one side, and on the other side, it drives all the segments of the liquid crystal display. Its interface is pretty simple. It has a register select input, which is more or less a 1-bit address that selects between commands and data to be displayed. It has a read-write input, which selects whether we want to read from the display or we want to write to the display. It has an enable line, which is more or less like a clock. And then it has 8 data bits that are used to transfer data back and forth. And everything below is connected to the liquid crystal segments. And further back, the datasheet shows how exactly you're supposed to talk to the display. To write to the display, we're supposed to set the register select and read-write lines, then pull the enable line high, apply our data, and pull the enable line low and make sure that the data is valid while the enable line drops, because the data is latched in on the falling edge of the enable, and then we're basically done. And the read works almost the same. We're supposed to set the register select and read-write signals, pull the enable high, which will then cause the display to produce the read data at its output, and then we drop the enable back low again, and we're done. The datasheet also mentions the bus timing and timing constraints that the interface has. For example, when we set the register select and read-write lines, we're supposed to wait a brief period of time until we pull the enable signal high. This is called the address setup time, and the datasheet lists it as 40 nanoseconds. And similarly, there's a setup time for the data. Before the falling edge of the enable input, the data has to be stable for a certain period of time. And this data setup time is 80 nanoseconds. There are also 2 hold constraints. After the enable signal goes low, the address lines have to be held stable for 10 nanoseconds, and the same for the data lines. The data hold time is also 10 nanoseconds, which means after enable goes low, the data and the addresses can change for another 10 nanoseconds. There's also a pulse width constraint here, which requires us to hold the enable signal high for at least 230 nanoseconds. And there's an overall cycle constraint of 500 nanoseconds, which means we have to wait 500 nanoseconds between activations of the E input. A read operation is pretty similar. We have to wait the same 40 nanoseconds between setting the address inputs and pulling the enable signal high. And then once the enable signal goes high, there's a data delay time of 160 nanoseconds maximum, which is the time it takes the display to produce the read data at the output. And that read data will stay valid while the enable signal is high, and when the enable signal goes low, there's a data hold time of at least 5 nanoseconds, which is the time after the enable signal goes low that the display will hold the data steady until it starts changing again. And also here we have the same 230 nanoseconds pulse width constraint and the same 500 nanoseconds total cycle time between adjacent activations of the enable. So to interface with this display, we apply the address, pull enable high, and then pull enable back low. When we're writing, we should apply the data as soon as possible. And when we're reading, we should make sure that we do something with the data just before the enable goes low. Doing this in a single clock cycle on my CPU is going to be pretty challenging though. At the beginning of the clock cycle, the outputs of the program counter, the registers, the program ROM, and the decoder are all stable. And they remain stable briefly after the rising clock edge. This is called the contamination delay. It's the time between when you change an input to when you first start to see a change in the output. The clock causes the program counter to change and the program ROM as well, because we have the clock connected to one of the program ROM addresses. And then the decoder starts to change in response to the program ROM changing. After a short amount of time, the program counter and the registers stabilize. This is called the propagation delay. That's the time between you changing an input and the outputs fully stabilizing in reaction to that change. And once the program counter output is stable, it will take the program ROM some time to have its output become stable. This is the propagation delay of the program ROM itself. And once the program ROM outputs are stable, the decoder will take some additional time to stabilize. This is the propagation delay of the decoder itself. At this point, the outputs look pretty stable, but remember that we're double pumping the program ROM. We use the first half of the clock cycle to read 1 byte from memory, and then the second half to read the other byte from memory. So the data produced by the program ROM at this point is only half the data we need. So this is basically garbage, and the decoder will produce some random outputs from that. And so after the clock goes low, the program ROM will start to change its outputs again because the clock is connected to one of its address inputs. And then in reaction to this change, the decoder will also start changing its outputs. And it again will take some time for the program ROM's output to stabilize, this time with the actual 2 bytes that we read from memory. And then some more time for the decoder to react to this new output from the program ROM and produce the decoded signals. And at that point, we've reached the end of the clock cycle, and the clock will go high again and start the next clock cycle. In this entire clock cycle, the only part where the CPU signals are actually stable is just before the rising edge of the next clock cycle. But the data is completely invalid in the first half of the clock cycle because we're doing this double pumping, and because the program ROM and the decoder flash memories are pretty slow, it takes quite a time to stabilize these signals. So if we run the CPU at the high speed, we're probably going to push up to the propagation delays of these ROMs. And so this period of time before the rising clock edge where the signals are stable is going to be pretty short because we want to be right up against the speed limit. And if we wanted to communicate with the liquid crystal display in a single clock cycle, this would look roughly like this. And there were some timing constraints here. For one, we need to apply RS and RW at least 40 nanoseconds before we pull the E signal high. Then we have to make sure that the data is stable at least for 80 nanoseconds before we pull E low again. Then we have to hold the data stable after we pull E low for at least 10 nanoseconds, hold RS and RW stable for at least 10 nanoseconds, and we have to make sure that the E signal stays high for at least 230 nanoseconds. And overall, between activations of E, we have to wait for 500 nanoseconds. Generating this signal pattern with all these timing constraints upheld is going to be pretty difficult to do in a single CPU cycle. The CPU internal signals are only going to be stable and valid at the end of the clock cycle, so these signal changes up here in the middle of the clock cycle are going to be almost impossible to generate. So instead of doing this in a single clock cycle, we can try to spread this pattern out across multiple clock cycles. To simplify this a bit, let me align the falling edge of E with the point where data starts changing again. This 10 nanosecond hold constraint is going to be easy. Most of the registers and latches in the design already have a propagation delay that's longer than 10 nanoseconds, so it's going to be easy to delay data by a sufficient amount of time. And in a similar vein, we might as well keep E and the data signal stable until the end of the clock cycle, together with RS and RW. And then I think it would be a good idea to drive all of these signals either from a register or a latch. That means that they only change on the clock and are stable otherwise. So we can just spread this entire timing diagram out across multiple clock cycles, for example, 3 clock cycles. And so RS, RW, and data come from the decoder and the registers, and as we've just seen, they become stable somewhere at the end of the first clock cycle here, and we can then use a latch to hold them stable afterwards. And then let's delay the rising edge of E to the next clock cycle such that we have enough time between RS and RW being applied and then an E going high. And I think this waveform would work in the CPU and it would be pretty easy to generate. But let's think about how these timing constraints affect the clock speed. This constraint between when we apply RS and RW and we pull E high means that the clock cycle needs to be at least 40 nanoseconds long. That's not going to be a problem because 40 nanoseconds is 25 megahertz. And it's going to be difficult to reach 25 megahertz with some of the chips we have. The slowest chip is the flash ROM we use as the program memory and the decoder, and that has a propagation delay of 70 nanoseconds. So if we put registers just before and after that, we would reach 70 nanoseconds as the shortest clock period we could have. But then there's this constraint on the pulse width of the E signal, where we need to keep E high for at least 230 nanoseconds. And at the moment, because this happens in one clock cycle, that would mean we would limit our clock period to at least 230 nanoseconds, which is just 4.3 megahertz. And I suspect that the CPU would actually run faster than that. So let's try to get this down to below 70 nanoseconds, such that we're not slower than the slowest chip that's already in the CPU. Spreading this out across 2 cycles would be 115 nanoseconds. 3 cycles would be 77 nanoseconds, pretty close, but let's push it to 4, which would be 58 nanoseconds lower bound for the clock period, which is pretty good. And similarly, there's this 500 nanosecond cycle time constraint. Right now, these 500 nanoseconds are spread across 6 clock cycles, so that's 83 nanoseconds lower bound for the clock, which isn't too bad. But let's increase this. 7 clock cycles would give us 71 nanoseconds, and then 8 clock cycles would give us 62 nanoseconds. And we can even go up to 9 clock cycles, such that the E-signal is nicely symmetric with 4 low cycles and then 4 high cycles, while the data and RSRW are stable. And I think this is what we want to build. The signal pattern meets all the timing constraints and it doesn't slow down the CPU. And to make initial experimentation easier, we could also just shorten this to 2 low and 2 high cycles on E. So let's have some fun and build a circuit on a breadboard that can generate this waveform. I'm going to use the 74HC163 chip. This is a 4-bit binary counter that has a bunch of inputs that lets us reset it to 0, load a fixed value into it, or disable counting altogether. Let's see if we can get this thing to count as a first step. The chip has a clear input to reset it back to 0. This is active low, so let me tie that high. We also have a load input, which allows us to load a fixed value into the counter. This is also active low. Let me tie that high. And we have 2 enable inputs, enable P and enable T. Let me tie those high such that the counter is just always counting. And then let's use a bunch of LEDs to look at the count. Let's power this up. And then let me connect the clock of the counter to my clock generator. And when I run the clock, this will repeatedly count through the values 0 to 15. Let me connect the reset of the clock generator to the clear input of the counter. So when I reset the CPU, this will clear the counter back to 0. Right now, this keeps counting all the time, but that's not what we want. We only want the counter to run if the CPU wants to write something to the LCD, because that's when we want to generate these waveforms. And once we're done, the counter should stop. To do this, I'm going to connect this enable line down here to the topmost bit of the counter. And since the topmost bit of the counter is currently low, the counter will be disabled. It's not counting at all. Let me now connect the value 1000 to the data inputs of the counter. And when I enable the load line by pulling it low, the counter will reset to this value 1000. And since the topmost bit is now set, the counter will be enabled and it will count up all the way to 0, where it will stop again. In this way, we can trigger the counter and make it count from 8 all the way up to 15 and then back to 0. Those are 8 clock cycles, which is perfect for the waveform we're trying to generate. But since we're toying around on a breadboard, I think I want to make this a bit quicker. So instead of counting from 8 all the way through 15, let's start at 12 and go all the way through 15, which is just 4 cycles. So this allows me to load the counter and then step through the values 12, 13, 14, 15, and 0, and the counter stops there. One thing we need to fix though is that when I pull the load line low, the counter will just be stuck in that loaded value and it will not count until I pull the load line back high again. But from the CPU's perspective, it would be nice if we could keep that load line low while the counter is running. An easy way to fix this is to use an OR gate and OR the load line with the topmost bit of the counter. That way, whenever the counter is active, the topmost bit is set, that will override the load signal and make the load input go high immediately, such that the counter can do its thing. I'm going to use a 74HC32 chip, which has 4 OR gates. Let's take the load line from an OR gate output, connect one of the inputs to our busy signal, the topmost counter bin, and the other input will become our active low enable signal for the circuit that the CPU can control. Let me maybe add an LED for that, such that we can see when the CPU enables the circuit. Currently this enable line is inactive, so the LED is off, which means the counter does nothing when I run the clock. But now when I activate that enable line, the LED goes on, and when I toggle the clock, the counter loads this initial value 12. But since the counter is now active and the topmost bit is set, even though we're holding this enable line, the load line has gone low again, and when I toggle the clock, the counter keeps counting. And since it's now back at 0 and in inactive state, toggling the clock will cause the counter to load again and then go through its cycle again. So even though we're continuously enabling the circuit, it will properly count and not get stuck at that loaded value. But even if we load the counter and start the pattern, but then decide to no longer enable the circuit, the counter will still run through its counts undisturbed and then get stuck in the idle state. All right, pretty sweet. So now we have a counter that steps through 4 distinct cycles whenever we trigger it. And in the timing diagram, we've determined that we want the enable signal to be low for 2 cycles and then to be high for 2 cycles. And in fact, this is exactly what the second counter bit is doing. It's low for the first 2 cycles and then high for the second 2 cycles. So we can just hook up the enable signal of the LCD to this second bit of the counter. Another thing we need is while the counter is running and generating the E-signal waveform, we need to make sure that the RS, RW, and data inputs to the LCD can change and remain stable. I'm going to use 2 74HC573 latches for this, one for the RS and RW signals and the other for the 8 data bits. We want these latches to accept new data when the counter is idle, when the topmost bit is 0, and we want them to latch and hold on to the value whenever the topmost bit is a 1 and the counter is active. That means we want to connect the latch enable inputs to the inverted version of this busy signal, the topmost bit. We don't have that yet, so I'm going to use a 74HC00 chip with 4 NAND gates to invert the signal. And I'm pretty sure we'll use a bunch of NAND gates in other parts of this circuit later, so this is going to be useful. Let me feed the busy signal through one of the NAND gates to invert it. And then we'll connect that idle signal that comes out of the NAND gate to the latch enables. This makes the latches transparent when the counter is idle, but then hold on to the last value once the counter is counting. Let me add an LED to show this busy state, because we'll remove that bar graph LED later. Now let me add 3 LEDs to indicate the state of the enable RS and RW signals we sent to the display. I'm going to use that idle signal as the low side of the LEDs, that way the LEDs will only turn on when the counter is active. And then let me make the left LED the RS signal and the right LED the RW signal. And the LED for the enable signal I'm going to add at the top. I'm going to continuously enable the output enable line for the latch that has the control signals, RS and RW. And now if I set the data inputs of the latch to high and toggle the clock, you can see the RS RW values being latched in. And when I change the inputs, these signals we send to the LCD won't change because the latch is in latching mode. And this remains stable until the counter resets and loads the next value for RS and RW. Very nice, pretty good. And you can also see that the red busy LED goes on immediately, but then the enable line stays low for 2 cycles. So this is cycle 1 and 2. And then in the 3rd cycle, the enable line up here goes high for 2 cycles before the communication stops. That's pretty cool. So we have these control signals that get stabilized by this latch. And then over here, we have the same latch again, which we'll use for data. The data latch also has an output enable, but we only want to enable that when we're doing a write, which is when the RW signal is low. When we're doing a read from the LCD, which we're not implementing yet, but we will in the future, then that latch can't drive its value onto the bus because that would collide with what the display is trying to write. So that output enable gets connected to the RW signal. Let me set all the data inputs to 0 for now. And then it's time to hook up the LCD. Let me hook up a few of the data lines first. Before adding all of them, let me connect the ground terminal of the backlight. And let me hook up power and ground. The enable line we can take from up here. Then we also have RW and RS. And the remaining data connections. And that leaves us with 2 remaining connections. There's a contrast voltage input here, which we need to connect to a potentiometer, and the positive terminal of the backlight, which I would also like to connect to a potentiometer so we can tune the backlight intensity. I'm going to use a 10 kilo ohm potentiometer for the contrast voltage between power and ground, and the 1 kilo ohm potentiometer for the backlight. And then let's power this up. That looks pretty good. The backlight goes on and we see something on the display. Now these 4-line displays use a 2-line display controller internally, and they just halve the lines and stack them above each other. This controller by default comes up in single line mode, which is why you can see all the characters on what the controller thinks is the first line light up more intensely than the rest. So let's send some commands to this. Let me step out of reset. First we need to send the function set command. This has bit number 5 set. We want to set bit 4 to indicate that we're using all 8 bits of the interface. These displays can also run in a 4-bit mode. And we want to set bit number 3 to change into 2-line mode, which is going to be 4 lines on this display. Our circuit is already enabled, so I can just step through this, and because we're switching into 2-line mode, the bars disappear from the display. Very nice, that seems to be working. Then we want to send a display control command. This has bit number 3 set. Then we want to set bit 2 to turn the display driver on. Also set bit 1 to turn the cursor on. And set bit 0 to have a blinking cursor. And when I send this command, you can see that the display turns on with the blinking cursor. And with that, the display is all configured. Let me also send a clear display command. It's not really needed because the display is clear and we're in the home position, but it's good practice to do so. Clear display is pretty easy. It has the lowest bit set and all the other bits are 0. And if we had any junk on the display or the cursor would be somewhere in the middle, this would return the cursor and completely clear the display. Let's write some text now. To send data to be displayed instead of commands, we have to set the register select signal high, and then let me set the data input to hex 48, which is the capital letter H. When I now start the transmission, you can see that the RS control line goes high to indicate data. And we get the letter H here on the display. Pretty cool. Let's do a lowercase I, which is hex 69. And finally hex 21 for an exclamation mark. That's pretty exciting. We can send commands and data to the display. And we also have this control line here. When I turn that off, we can let the clock run and the display won't do anything. And when I turn it on, the circuit writes to the display continuously as fast as possible. Let's go and hook this up to the CPU. First, let me connect the LCD to power. And then we have 3 control signals that we need to hook up to the CPU. First is the enable signal. I think I'm going to connect that directly to the instruction decoder. We already generate this functional unit select signal, and I think we'll just assign unit number 3 to the LCD. The RS signal I'll connect to the functional unit opcode bit 0. And the RW signal I'm going to connect to functional unit opcode bit 1. The LCD circuit also needs a clock and a reset signal. And then last but not least, the data we're writing to the LCD, we want to come from the RD1 port on the register file, basically the first register operand. And we'll also need the clock generator hooked up. That was pretty straightforward. Now let's go and write some software for this. First, let's define a few new instructions. Let me call these the control and status register instructions. This is going to be a grab bag of registers and register-like things in the CPU that you only occasionally need to read and write. We'll need 2 instructions. The first is going to be an LCD command write instruction. This only reads the RD operand and then writes that data as a command to the LCD. And second, we also need an LCD data write instruction that does the same thing but for data. Let me set the lowest 4 bits to 0. This is going to be the same as our branches and some of the other basic instructions we have. In the topmost 4 bits, the branch with register offset has the value 2, and the branch with register has the value 3. So let me pick the value 4 for these LCD write instructions. And since we're not using an RS operand, we can use bits 8 to 11 to encode whether this is a command write or a data write. And bits 4 to 7 are going to be the destination register. Then let me add these instructions to the decoder. The LCD is functional unit 3. Our LCD instructions have the function 0 field set to 0. Then the function 1 field is the value 4. And the function 3 field is either 0 or 1, indicating whether it's a command or a data write. And the decoding is pretty straightforward. We just want to read the RD operand. We want to throw this at the LCD functional unit. And as a functional unit opcode, we'll just forward this function 3 field, the 0 or the 1. Remember that we've connected the RS, the register select signal of the LCD, to bit 0 of the functional unit opcode. So by setting that to 0, we'll do a command write, and by setting that to 1, we'll do a data write, just as we specified in the instruction set architecture. Let me regenerate the ROMs. And then let's add these instructions to the assembler. First, I'll use them in the test program. This then makes the assembler fail. To fix this, these instructions need an opcode. We need to be able to parse them. And print them back in human readable form. And finally encode them in their binary form. And this now allows us to compile the test program again, and the LCD command and data write instructions appear in the output. And now to give the display a proper test, let's write a program that prints something on the display. I'm going to steal the first few lines from the Fibonacci test program. And then we need to initialize the display. First, we need to send that function set command. This command has bit number 5 set. Then bit number 4 we want to set to a 1 to indicate that we're communicating via an 8-bit interface. Bit number 3 we want to set to turn on 2-line mode. And bit number 2 indicates the font, and we're going to set this to 0 to have the usual 5x8 font. This will configure the display, and this LCD command write will take 4 cycles to fully go through. So let me add a few knobs. If we try to write to the display while it's busy, the write will just be lost and never execute. Next, we want to clear the display, just in case there's any garbage there. This command is pretty easy, just has the lowest bit set. This LCD write up here takes 5 cycles to execute. Basically 1 cycle for the LCD write and then 4 cycles for it to fully complete. But since we're doing a load immediate here before we write to the display again, I can delete one of the knobs because we only need 4 instructions separating the LCD command writes to make sure that they are 5 cycles apart. And then finally, let's turn the display on. This command has bit number 3 set. And then bit number 2 indicates whether the display should be on, so we want to set this to 1. Bit number 1 indicates whether we want the cursor. Let's set that to 1 to get a cursor. And bit number 0 indicates whether the cursor is blinking. Let's set that to 1 as well. Pretty nice. At this point, the display should have initialized, cleared, and turned on, and we should see the cursor blinking, just the same as when we sent the commands manually before. Then let's write hello to the display. First, we're loading the ASCII code for the capital H into R0, and then we're doing an LCD data write of R0 to the display. And then let's do this for the remaining letters. At this point, we should have the word hello on the first line of the display. Let's also try to do this in a loop. Let's maybe go to the second line and then write the numbers 0 to 9 onto that second line. To go to the second line, we have to use this set display data RAM address command. This lets us set the current cursor position to any address in the small internal memory of the display. Now these displays are a bit weird. The first line starts at address 0 and the second line starts at address hex 40. And since we want to go to the second line, we have to set the address to hex 40. And then let's write the digits 0 through 9 using a loop. First, we load the ASCII code of the digit 0 into R0. Set R1 to 10 as our counter. Then we write R0 as a character, increment the ASCII code of our character, decrement the counter, and then loop back until the counter hits 0. And this knob here adds as padding to ensure we only have one LCD data write per 5 cycles. And then at the end, let's clear the registers again and halt the processor. Let's see if we can compile this. That seems to work. And this indeed looks like the program we've just written. Let me compile this to a binary. And then write this to the program memory. Let me plop down the flash ROM again. And then reset the CPU. The first few instructions clear the registers and the flags. And now we're configuring the display. We're loading the function set command into register R0. And then we're doing a command write to the LCD from register R0. And the decoder picks functional unit 3, which is the LCD, and correspondingly the enable light goes on the LCD control circuit. This means that when I hit the clock, the LCD control circuit becomes busy and starts sending the function set command. E is low in this first cycle, and also the second cycle. But then in the third cycle, E goes high, and it remains high. So the LCD control circuitry is in the last cycle of sending that command. And in the meantime, the CPU is loading the next command into register R0. This is the clear display command. And so at the same time as we're writing the new value into the register file, the LCD control circuitry will finish sending its command. And we'll see the display switch into the correct mode where these bars then disappear. And yeah, there's the new value in register R0 and the display has changed. So as a matter of fact, there's a very lightweight out-of-order execution happening where the CPU can load new values into the register file while the LCD is busy still executing that write. Now we're doing an LCD command write again. You can see the LCD is selected again, the enable signal is high, and we're going to execute this command 1 to clear display next. This is again the last cycle of this communication, and while the LCD is finishing in this cycle, the CPU is already preloading the next command, the command that turns the display on, into register R0. So the LCD becomes idle again. There's the display ons command in register R0, and we're again doing an LCD command write. The LCD is enabled again, and when I step through the clock cycles, the display turns on with the cursor enabled and the cursor in blinking mode. Now the program is going to write some text to the display, and in fact, while the LCD was finishing turning on, it has already preloaded the capital letter H into register R0, and over the next few cycles, the string hello appears on the display. Pretty nice, so we can print messages to the display. Next up, the program prints the digits 0 through 9 to the LCD, and it has already preloaded this set display data RAM address command for the LCD into register R0. This is going to move the cursor that is currently at the end of the hello string down onto the second line. So let's get that command started. And now, while that command is executing, the program is already going to set up this loop that writes the numbers out. First, we're going to load the ASCII code of the digit 0 into register R0, and then we're going to preload register R1 with the value 10 because we want to write 10 digits. And as you can see, in the meantime, the LCD has also finished executing that display data RAM address setting command, and it's now moved the cursor to the second line. And now we're doing an LCD data write, writing the digit 0, which is in register R0, to the display. And then the program keeps incrementing the ASCII code and decrementing the counter and write the digits 0 through 9 to the display and then halt. Very cool, this works like a charm. It's really nice to have a way to finally print things to a display, which is going to make writing programs a lot easier, and it's going to be easier to figure out if the programs do the right thing when we don't have to look at the binary patterns in registers. And with the circuitry basically writing to the display in the background, we get the first taste of out-of-order execution, where the CPU can do other things while this display circuitry is running. The big problem right now is that the CPU can actually issue these LCD write commands faster than the LCD can process them. If we issue 2 LCD writes back to back, the first one will start, but then the unit up here is busy, and the second command would just fall through the cracks. And it would also be good if we could read back from the display. The LCD allows you to read back the current address you're on, so you can figure out where the cursor is at the moment. And it also has a busy flag for long-running instructions such as a clear display, which may take multiple milliseconds. It pays off to pull that busy flag and check if the display is actually ready. In the next episode, we're going to look at pipeline stalling, where we can stall the CPU and prevent it from making forward progress. And we're going to look at back pressure, where units like the LCD circuitry up here can provide back pressure if the CPU is requesting another operation too soon while the unit is not ready. And this will allow us to prevent the CPU from overpowering the LCD circuitry here. And when the CPU wants to read something back from the LCD circuitry, we can force the CPU to actually stall and wait until the data becomes available. And that will get us quite a significant step closer to proper out-of-order execution. Can't wait for that to happen. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.